Okay, we are live.
Okay. Hi, everyone. Welcome to the second installment for this GPU/ScaleML session. Today, we have excited to have Guangxuan from MIT to tell us about efficient streaming LLM model with attention sync. Just a little brief introduction for Guangxuan. Guangxuan is a 4th PhD student, a candidate at MIT, advised by Professor Song Han. So his research interests focus on efficient algorithm and systems for deep learning, with a particular emphasis for large foundation models. His work has been widely recognized, accumulating over 10,000 stars on the GitHub and having a lot of impact, including GPT-OSS, as we shall see. So key to some of the projects, some of the early work included Smooth Quant, StreamingLLM had been integrated into major industry tool chains, including NVIDIA TensorRT, TensorRT LN, Hugging Face Transformers, and many others. And then Guangxuan, please take it away.
Okay, thank you. Thank you, Han, for the introduction, and thanks for having me today. So, hi everyone, I'm Guangxuan Xiao. I'm very happy to present our work, which came out 2 years before. It's called Efficient Streaming Language Models with Attention Sinks. And why we're discussing that today, because it becomes a topic recently, because the GPT-OSS just came out, and if we look into its technical report and GitHub repo, we can find a very interesting design called attention sinks. So actually, this phenomenon is named in our paper 2 years ago. So it becomes a really reignite people's interest, and people become very curious about it. So it's very nice to be here to talk about how it's developed and the history behind the attention sink and what's the original research on that. So to briefly introduce the attention sinks in GPT-OSS, so it adds one learnable scalar per head called attention sink for enabling the model to pay no attention to any token when needed. So it's just literally the words in the technical report. So so on the right, it's a figure by a blog post by my friends. It's really nice. So in its code, you can see that there is a sync parameter to pass into the attention function. So when computing attention, we will append a column of number, which is a scalar for each head, and a learnable scalar. And when we are computing the attention probability, we compute the softmax over the sync plus all the tokens, attention logits. And then after computing the probability for the tokens, we remove out that column, so it's not involved in the final computation. So what does this give is that it enabled the each row's probability not add up to 1, so that you can pay no attention to any token when there is anything you need to attend to. Yeah. So the motivation of our original research was that, so in 2023, we have Llama 1, and in the summer we have Llama 2, and these models are usually having like 2K to 4K context length. And I was thinking about building chatbots that can chat with you all day long. So for example, if we are building some companion bots, we don't want the model to raise some error like token limit is exceeded or out of memory when we chat with it to a certain period. So that will be a very bad experience. So that's the motivation of our work, which is all day long and like streaming like multi-round conversations. And we term these applications called long streaming applications, where long interactions are needed. So, but when applying language models on these streaming applications, there are two main challenges. So the first one is, which can be depicted in the very nice figure here. So we can just look into the orange lines, orange solid line and the orange dash line. So the first challenge is the extensive memory usage during the decoding stage. So we can check the orange dashed line here, which correspond to the y-axis on the right, which is the GPU memory usage. So the orange dashed line is the GPU memory usage of naive transformers, which is language models. And you can see that when x-axis is the input sequence length, and when the input sequence length increase, there is a linear increase on the GPU memory usage. So the longer you talk, the more GPU memory you need. And to a certain extent, you don't have infinite GPU memory. So to a certain extent, you will exceed the GPU memory limit and raise the out of memory error. That's the hard limit by the GPU. And the second inability is that these models are trained on fixed chunk of pre-training corpus. So we pre-train these models on 4K sequences, like Llama 2, they pre-train on 4K sequences. And you can see that when the input sequence exceed 4K sequences, there is a huge spike on the perplexity, which is the solid line. So perplexity is a measure of the output quality with the ground truth. So the lower the better. So if the perplexity shoot up, it means that the model output can no longer be trusted, and it's no longer even natural languages. So that means that we cannot deploy these models on sequences longer than the pre-training limit. So even if your GPU can hold 4K sequences, you cannot deploy these models on sequence longer than 4K because your model haven't seen them. And here is the demo. So before we introduce all the technicals, and today we want to show that if without StreamingLLM, what will the streaming application be like, and what's our final quality and the application achieved by StreamingLLM. So on the left is without StreamingLLM, you will see that the model, we give the model a bunch of questions, and we let the model to answer each question. So we give a very long list of questions, and after each question, we let the model decode. And you can see that the model first, the quality-wise, the model performance breaks. So the model start to output some nonsense tokens like zeros and comma, semicolon, and these just not language. And second, after a while, because the model is still running in the background, and it will have a linear increase of memory usage, and so that to a certain extent you will reach to the GPU memory limit, so that we will see the out of memory error. But with StreamingLLM, we can see that the model continues streaming with very good quality. The model can still serve us, and so no matter how long the interactions are. So here are the two screenshots on the failure of if we naively deploy language models on the streaming application. So you will see either model performance breaks and or out of memory error, or both. So to start off, we can review one of the very important optimization techniques in deploying GPT-like models. So in GPT-like models, it's autoregressive language modeling. It means that the previous states are not depending on the future states, which means that you can actually cache any states you encoded of the previous tokens and reuse them when decoding later tokens. That's a very powerful technique called, very basic also, technique called KV cache. So that here is an illustration from Trainium. So illustration is that when you have I love token in the context, you don't have to recompute the keys and values of them. You only need to compute the QKV for the new token Trainium, and then you can compute the attention score over the entire context without recomputation. Then here is a more animated illustration on this. So if you don't do KV cache optimization, at each step you need to compute a quadratic Q multiplied by K matrix multiplication, which is, so in total, which is n cubic complexity, which is not feasible in real world applications. And if you have KV cache at each stage, you only need to compute one row in the attention matrix, which means that the overall complexity is n quadratic. So it's a huge saving. But here is a problem. So when we are deploying language model on long contexts, we can the KV cache can be very large. So it can even exceed the model size itself. So let's still use the Llama 2 model as an example. We can very exactly calculate how much memory that requires to store the KV cache. So the KV cache size equals to batch size multiplied by number of layers, multiplied by number of KV heads, multiplying by number of the hidden dimension per head, multiplied by the sequence length. And since you need to store both keys and values, so multiply another 2. And if you don't do any quantization, if you store them in 16 bits floating point numbers, that's 2 bytes per number. So in total, it will be half megabytes per token. So now these days, people have optimization techniques like group query attention and all kinds of techniques to optimize it. It's still pretty big comparing to storing raw text in computer. So when you store a token in computer, it usually takes several bytes. But here you need megabytes level storage. And now we can calculate the KV cache under a common setting like batch size equals to 4 with respect to different sequence lengths. And you can see that this KV cache requirements grows very fast, and it can outpace the model weights very quickly. So when we are deploying the sequence like 32K on a 32K sequence, the KV cache requires 64 gigabytes, which means that we can we will use like A100 or H100 to serve this model. So that's very expensive. And another approach, a very natural approach, is that since we see a very drastic usage of memory and decoding time, how about we just evict some token in the cache and only attend to a constant number of tokens? So here is a very natural approach called window attention, and which means we only cache the most recent key and value states. And for when we're decoding the T's token, so in the figure on the left, when we're decoding the T's token, we only attend to the L recent tokens and evict the previous T minus L tokens. So this reduced the memory complexity to L instead of T. So when L is a constant, since L is a constant, not growing, we have constant memory usage. And during each step, we also have a constant decoding time because the context is no longer growing. But when we benchmark this method on natural text, we found that the model collapsed very drastically when the text surpassed the cache size. So previously, when we naively deployed the language models on longer sequences, the model collapsed when the sequence grows longer than the pre-training length. But now we see the model collapse when the text is longer than the cache size. So this is very interesting. So in the figure, we depict this in the figure on the right. So x-axis is the input sequence length, and the y-axis is the log perplexity, which is perplexity. And it's still the lower the better, and it's a measure of the quality. And you can see that for the orange line, which is window attention, we can see that when the sequence length is longer than the KV cache size, suddenly we see a perplexity spike, which means that the model can no longer be used. And if we think that very carefully, we will realize something is happening in the model, which is when the sequence length goes beyond cache size, it means that first tokens are evicted in the window. So as soon as the first several tokens are evicted from the window, the model can no longer function well. So that's a very interesting and important observation, which motivates the following study. And there is another. So we already discussed two baselines. One is dense attention. We already discussed it has very bad computational complexity and memory requirements. And when the sequence length goes beyond the pre-training text length, it gives very bad perplexity. So we can, in efficiency-wise and quality-wise, we cannot deploy models with that attention. And for window attention, we have good efficiency for each decoding step, but we don't have good quality because when the first several tokens are evicted, we have bad quality. And there's another approach, which is like an Oracle baseline. We call it sliding window with recomputation. And the overall idea is that we don't use KV cache. We just recompute the most recent L tokens representation when decoding a single token in the last. So that gives us the best quality because it's aligned with the pre-training setting, and so because the model is pre-trained like this, but the previous tokens are truncated, but it gives us a very bad efficiency because for each step, when we are only need to decoding one token, we need to compute a quadratic attention matrix for that token, which is very costly. And it gives a good perplexity, but it gives a quadratic complexity per step. So let's delve into why window attention fail and why evicting the first few tokens are so important to the model. So we visualize the attention matrix within the model, and we see the attention sink phenomenon. So the observation is that the initial tokens have very large attention scores, even if they are not semantically significant. What does that mean? So we visualize the attention scores in Llama 2 7B models, and you can see that beyond layer 2 and layer 1, so the bottom two layers, beyond the bottom two layers, we found all attention heads, all the tokens significantly attend to the first token, no matter how far they are from the first token. So in these cells, because it's causal attention, the upper triangle is gray, it's masked, and each cell means the attention strength one token paying to the other. The redder, the higher, and the bluer, the lower. So we can see that there is a very solid red line in the first column in the layer beyond layer 2. So it means that all tokens very strongly attend to the first token, no matter how far they are. So this is very intriguing, but it actually explains why window attention fails. Because if we explicitly write the softmax function into the form below, we explicitly get out the first token's attention score in the denominator. We can see that if that value is super large, when we're evicting that token, it means that we significantly change the distribution of the softmax. So it means that the model's attention distribution is no longer the same as the pre-training stage. So the model will not be able to adapt to this, so it will collapse. Yep. And so we term this phenomenon as attention sink, because as these tokens are like sinks to attract these models disproportionately dump some attention irrespective of the relevance of the first tokens. And we also want to understand why attention sink exists. So the explanation in our paper is that softmax function limit the enforce all attention scores have to sum up to 1 for all contextual tokens, even if for some tokens they don't want to attend to any of the tokens, and or for some easy tokens they don't have to attend to a lot of tokens to decode. The softmax function still enforce all the tokens to have sum up to 1 attention probability. So in that case, the model has to learn to dump the unnecessary attention score to some of the tokens to attention sinks. So for causal language models, it's very natural for the model to use the first several tokens as attention sinks, because since the model is causal, these tokens are almost globally visible. And if you don't use the first several tokens as attention sink, but use some tokens later, the model, for tokens before that token, it cannot leverage that token as attention sinks. So it's most rational for the model to use initial tokens as attention sinks, because we're doing autoregressive language modeling. And another ablation study is that if it's because the several tokens are semantically important for the model to dunk the attention on them, because they usually become some crucial or summarization tokens, our answer is no. So in the table below, we measure several settings. So 0 plus 1024 means window attention. We use 0 starting tokens plus 1024 reason tokens to do like sliding window like decoding. And when we measure the perplexity, it gives us a very large perplexity, which is very bad. And we preserve the initial 4 tokens along with the most recent 1020 tokens. And then we measure the perplexity. It gives us pretty nice, which is 5.4, close to the pre-training perplexity. And if we replace the initial 4 tokens to 4 line breaking tokens with no meanings, we still find that 4 line break tokens plus 1020 reason tokens still recover the model perplexity. So this concluded that it's not because the first several tokens are semantically important to make the model to highly relying on them, but it's because they're decoded they're encoded at the front, so they're initial tokens, so that models want to attend to them very strongly. So after realizing this phenomenon, it's actually very natural and very simple to propose a fix, which is StreamingLLM. Since these attention sinks, which are initial tokens, are super important, we just don't evict them in window attention. So our objective is to enable LLMs trained with finite attention window to handle infinite text lengths without any training or fine-tuning. And so on the left, we illustrate the attention map and the scheme of StreamingLLM. So the yellow column is the attention sink, which we always allow the model to attend to. And remaining is still the same as window attention. The model still can attend to the most recent L tokens, and the middle tokens are evicted. So this still gives us the same complexity as the window attention, because we still have constant memory usage and constant decoding rate. But since now we have the attention sink to ground the model, we have very nice perplexity, which is close to the pre-training setting, and we can slide very long no matter how far we are from the pre-training sequence length. And on the right is a closer illustration of how StreamingLLM work. So let's imagine a model with context length 8. When we are decoding the 7th token, the model is just doing full attention. And we are decoding 8th token. Since the model is only trained on 8 tokens, it has to evict some tokens. Now, instead of evicting the 0th token, we evict the 4th token, because we preserve the first 4 tokens as attention sinks. And we were decoding the 9th token, we evict the 5th token, and we preserve first 4 and the most recent 4 as in the cache. And here is another technical detail on how we assign position encoding in StreamingLLM. So it's a very important detail. So since the model is trained on a sequence of 8, when we're decoding the 9th token, we don't want any out of distribution thing happen. So since the model never seen number 8 and number 9 before, so we assign the position in the cache rather than in the original text, which means that we assign position encodings like 0, 1, 2, 3, 4, 5, 6, 7 instead of 0, 1, 2, 3, 6, 7, 8, 9. So the model will always believe that it's actually decoding the 7th token rather than decoding the 9th token. So this can be efficiently implemented by caching the position encoding before applying position, caching the KV cache before applying the position encoding, and afterwards we apply them back when decoding. So it's already supported in framework like llama.cpp and TensorRT-LLM. So here are some empirical results. So we compare StreamingLLM with dense attention, window attention, and sliding window with recomputation. And the conclusion and the results is basically we already explained them all. So dense attention, which is the blue line, is we can see it fails beyond pre-training attention window length. And for window attention, which is the orange line, we can see that it fails after the input exceeds the cache size. So when the initial tokens are evicted. And the green line is like Oracle baseline, which is for each step, we just recompute everything. And it almost overlap with the StreamingLLM perplexity. So the green line and the red line are together. So we have very stable performance, and the perplexity is close to the sliding window with recomputation baseline. And we scale up our experiments to super long language modeling and more models. So we scale up to Llama 2 7B, 13B, and 70B models, and more model families, including Pythia, Falcon, and MPT. And MPT here uses alibi position encoding, and for Llama 2, Pythia, and Falcon, they use rotary position embedding. So it means that StreamingLLM is also agnostic to position embedding settings. And we can see that with StreamingLLM, these models can now effectively model to up to 4 million tokens, far beyond the pre-training sequence length. And here is the efficiency results. We can see that the only feasible baseline is the sliding window with recomputation, which is the gray bars. StreamingLLM has similar memory usage as this baseline because they memory-wise they're the same. But for each step, we already mentioned that sliding window with recomputation has a quadratic complexity per step. So the longer the cache size is, the more speed up we have. So we can provide up to 22.2 speed up over this baseline when we are using Llama 2 13B on a sequence of 4096. So this makes LLMs for real-time streaming applications feasible. And also here are some ablation studies. So we find out that for models, some models, they are trained to use the initial several tokens as attention sinks rather than only the first token. So maybe because the first several tokens in the key representation, they are very similar. But we find that keeping 4 initial tokens for streaming is generally enough, and more tokens have very diminishing return. And for some models, only 1 tokens are enough. For example, here, maybe Pythia model, 1 tokens is enough. And furthermore, here is an interesting part. We want to explain why the model is trained with 4 attention sinks. Can we build a model with only 1 attention sink and preserve it to make streaming more stable, and so that it's like we already know during pre-training that we are going to use that token as attention sink. Can we pre-train 1 attention sink? And furthermore, can we use this idea to improve the pre-training, and which is demonstrated in GPT-OSS. So here are the experiments in our paper. So during I think concurrently, maybe a month before our paper come out, there is a very popular blog post called "Attention Off by One." So it's basically same observation that we want to allow the attention not sum up to one in some cases, and attention off by one give you well, a plus one denominator in the denominator, which can be equivalent as which is equivalent as you have all zero keys and all zero values in the KV cache. So we call that zero sync, and we also tested that in our paper. So here are the results. We pre-train small language models, sub 1B model, and for 140 billion parameters, for 140k steps. Sorry, and so we compare with no attention sync, which is the blue line, vanilla, and the orange line, which is we have a dedicated attention sync at the front. So we we always prepend one token in all training sequences, and we can see that the pre-training loss curve of with attention sync, it's slightly better. So it's converging slightly better than without attention sync, and they have so it at least it's not affecting converging. And when we benchmark the model trained with a dedicated attention sync on some downstream task, we can also see that the model improves, so very consistently improves on these benchmarks. And when we are doing streaming now, comparing to vanilla model, which use like 2 to 4 attention syncs, now we can use just one attention sync, and it gives us very stable streaming performance. And if we use zero sync, like the attention of softmax off by one approach, only keeping one token is not enough because the model is not fully leveraging the initial token, the zero in the front. It still needs 4 initial tokens to be attention sync, which means that if you give the model flexibility to not to have sum up to one attention, the model still needs to make some token attention syncs. But if you give the model a very flexible way, like learnable token as attention syncs, the model will know that will use that token to absorb all the attention and only use that token as dedicated sync.
By the way, there were quite a few questions in the chat. I'll let Hong go first.
Yeah, so I have a question. Yeah, so thanks, very nice presentation so far. So this is something covered in your blog post already, but I thought it would be nice to be covered in the live stream as well. Can you comment on the sort of the differences between the version you work on initially versus what say the GPT-OSS be using in your open source models?
Great question. So let's go to the GPT-OSS design. So it gives a trainable scalar at the front, or any places is the equivalent. So in each row, for the attention not sum up to one. So it's not attention sync token in our paper, and it's also not the off by one attention in the softmax off by one blog post, but it's like something between. So it gives a learnable scalar in the denominator. And in our, like, if you give the model a dedicated attention sync, it makes the learnable scalar more powerful because for each token you can have different sync values. So for some tokens, they may have larger sync values to attend to. They can attend to the initial token stronger, and for some token, they can attend to the initial token less. But it requires a dedicated, like if you do that, you need a very nice attention kernel to do that because you always need to attend to the first token, and also it will need some like data engineering because if it needs some data engineering because in your all sequences you need to pad one or replace the initial token in all sequences to be a dedicated attention sync. But if you use this sync approach in GPT-OSS or attention off by one, it's not intrusive. So almost you don't have to do anything related to data or kernels. You just need add one sync value in the denominator and remove it after computing the attention. But I still think that it needs some like very slight kernel modification, but it's not as large as if you have a dedicated attention sync.
So it's more like sort of it's almost probably get you what you would have do given what you know, but it's like a lot simpler from a sort of a engineering and a practical perspective.
Yeah, it's like a balance on the like flexibility and the amount of engineering you need to implement this.
Yeah, we have a couple questions. Yeah, sorry, Alex.
I can let Joe go first. Yeah.
Okay. Yeah. So have you looked at the GPT-OSS models attention sync values, like to see if there are some patterns that parallel the actual like original work you did with the attention sync with the initial tokens?
I haven't done this myself, but I saw some like Twitter posts or blog posts online. So people do some analysis on the amount of attention, and if I remember correctly, they do absorb a lot of amount of attention in the sync. Yeah, so they occupy a lot of attention. And in our paper, we also, if you check the StreamingLLM paper appendix, we check the amount of attention the first several tokens absorb, and almost take on average 70% to 80% amount of the entire attention.
Awesome, thanks.
Yeah, I'll ask some of the questions people are asking in chat. So Donghyun Ju asks, would it be correct to understand that the attention sync phenomena is observed in any models that use softmax?
Yeah, I'm going to present that. So yeah, I think I just get to this page. So attention syncs, it's happening in other transformers, and transformer is powered by attention, and attention is powered by softmax. So concurrently to our work, people also a group in Meta find basically the attention sync phenomenon in vision transformers, and they called it registers in VIT models. So basically, the difference between VIT and also the BERT, I also introduced BERT. We'll talk about BERT in this page. So VIT and BERT, they are bidirectional transformers, which means that the former the token before later tokens can see the tokens can see each other no matter the positions they have. So, but we still find that in some background patches, these researchers find out that in some low semantic background patches, these models have very large attention spikes and high norm tokens. So it's like attention sync happening in these low semantic background pixels, because they're very commonly like emerging, and the model needs some way to dump the attention into some tokens. And for BERT model and Roberta models, same wise, people already find out that I think around 2019 that and some tokens like the separator token and some delimiters like comma, period, they will absorb a lot of attention. So I think these tokens are basically serving as attention sinks in these transformer models.
Makes sense. Yeah.
Mm-hmm.
So Jay Lee has two questions. In real applications, we can prepend system prompts. So would this effectively solve the same problem as StreamingLLM?
Yeah. If basically you are using the system prompts as the attention sinks, and I actually think that's a better, a more elegant way to do that. So if you want to do very long chat, it makes sense that you always ping the system prompt KV cache in the context. And when you're doing something longer than the sequence, than the pre-training limit, you can sliding and evicting something in the middle and still attending to the system prompt and the local context. That makes a lot of sense.
And their second question was, if the position is the only factor that matters with attention sinks, is it possible to redistribute I'm assuming they mean probability mass over the remaining tokens during training.
Yeah, I kind of I didn't get the approach here, so it's very vague to. I don't know what does distributing probability mass mean during training.
We can. I also am not entirely sure, so maybe if they have a follow up for that. Yeah, Siddhartha Rao asks, basically, is there a study on like understanding how much like the probability mass gets distributed towards sinks? Yeah.
Yeah, I think it's like a feature that the model needs some bias or needs some tokens to absorb attention. And no matter how you redistributed the attention mass, it's like you're making the model not, you're preventing it from learning. So I'm not sure that if that's good or bad. Yeah, that's my like very, very initial thought.
I see. And I think there's two more questions. Sorry, there's a bit of a discussion, so I need to parse through. So yes, Besher asks, is there any particular type of tokens that have to be the sync, or are they basically the starter tokens?
Oh yeah, great question. So so people often ask me that whether the attention sync is just the begin of sentence token we found in these models, and the answer is no. So that's because when we're doing LLM pre-training, depending on your tokenizer design, it's usually adding the beginning of sentence token before we chunking them into small chunks to feed into model. So if you check the training sequences, most of these sequences are not starting with begin of sentence. So most of the sequences are starting with just natural tokens, and which means that the model learned to attention syncs on all tokens, not just beginning of sentence tokens. And how they learned it is actually very easy for models to figure out which token is the first token, because for first token, the model is just like a MLP. There is no context for the first token. So the model can definitely learn which token is the first token. And no matter what token comes, when the model realizes the first token, it will encode it to be the key of the attention sync. So the answer is not only BOS is attention sinks. Any tokens can be attention sinks.
And the last question was by Arseny. He asks, if you go back to the vision transformers example, in the VIT's need registers paper you referred to, they suggested that this was global information that the model was encoding. So are you suggesting that this is not the case?
Yeah, so there are different like interpretation on this. So for bidirectional transformers, these tokens can serve as like global register or some intermediate information store to help the model converge. But definitely for GPT models, attention syncs emerges not because of that, because in GPT models we find out that attention sync are initial tokens, and initial tokens can only store information by information about itself. It cannot see later tokens, so it definitely cannot be some like global information puller or intermediate register. So for different models, they may have different functionalities. But I think the most interesting part here is how attention syncs emerge. Maybe it's not because of the model wanted to serve as global information store, but it's because the model needs some way to not let the softmax distribution sum up to 1.
I see. Okay, that should be all the questions in the chat. So I think you can move on from here. Thank you.
Yeah, thanks for the questions. So I think it's I'm almost done. So the final thing here is that it's a limitation part. Like we are discussing, like some people may think that StreamingLLM gives you infinite context to chat, but that's not the case. So we benchmark the model's ability on synthetic tasks shown on the left. So after a few lines, we give the model a bunch of random numbers, and after a few lines, we ask the model what's the number several lines before. So for example, at line 10, we ask the model what's the number in line 0, and at line 10, we ask what's the number at line 30, we ask the model what's the number in line 10. So here, the token distance is 20 lines, like 20 lines here. So on the right is the model performance. So when we are asking the model something within the cache, which means the token distance is smaller than the cache config. When the token distance is 1840, when we are using like 4 plus 2044 setup, we have a non-trivial accuracy, which is 75.30. And if we have a longer token distance, which is beyond the cache, and we can see that if token distance is beyond 2048, we can see that all 0 accuracy, which means that anything evicted from the cache can no longer be retrieved. So, which means that StreamingLLM doesn't give you an infinite memory, but it gives you a very stable performance over very long input, and the model can always attend to the thing happening in the local, but it cannot remember things evicted. So we have some follow-up works on this to address this issue. So basically, we developed some smart evicting techniques, and or we don't even evict these tokens, and we only evict for crucial attention heads to streamline the model. So feel free to check my follow-up works. So yeah, so that's basically it. In conclusion, we propose StreamingLLM and using the attention sync mechanism to enable streaming deployment of LLMs. And feel free to check our paper, code, demo, and blog on the internet. Yeah, thank you so much for listening.
Yeah, thanks, Guangxuan, for the very nice presentation. Actually, I have some follow-up questions. So this paper's been out, I think almost 2 years. I'm curious, what are the things, in your opinion, that the initial draft paper got right? What are the things you think the initial paper that some of the prediction about the future, possibly you might want to revise some of the things going forward? What are the things you think your prediction got right, and what are the predictions? Given with a time of 2 years, what are the things you think you might have a different thoughts given what you know today?
I think basically all the claims are basically correct in my view right now.
Great, that's nice.
Yeah, so that's why I'm still talking about it.
That's fair.
Yeah, and it's very, maybe I should test whether adding a scalar training with a learnable scalar per head, it's can make sync phenomenon better, so that, which is exactly what GPT-OSS has done, and also several follow-ups work done. And basically, I think the intuition and the observation is correct. And maybe one thing I haven't do is the trainable scalar, and the second thing is I haven't scaled up these experiments to see if it's still hold or it still can benefit pre-training when we make the model parameters and the token numbers larger. But still, I think most of the claims are still holds these days.
Nice. Yeah. So I'm so curious, obviously, this is, once the project came out, it becomes very, you get a lot of attention and credit for doing this work. I'm curious, once the paper came out, does it change your own research direction about, for the past 2 years? When the paper came out, did it change your own research direction because of this?
Yeah. So that's basically the question I ask here. So after this work come out, a lot of people ask me. So the paper came out, it become very popular on Hacker News because someone posted like now we have 4 million contexts, and a lot of people misunderstood. And that probably be a reason why this paper is popular because of a lot of people misunderstood. But so people were thinking that it gives you infinite context, but I was still thought of I continue work on this problem to give you very long context very efficiently and without forgetting things. So that's how this work reshaped my research direction from like quantization to long context modeling. But yeah, I'm still working on this. It's still, I think, a very challenging task, but interesting to us.
Yeah, and also for people on the call, Guangxuan has like put out a couple of, I think 3 blog posts, really amazing blog posts going through, including one on attention sync, and did a couple others about various aspects of long context modeling, which I actually highly recommend people to take a look. Some of the things actually, including some of this about sort of your thoughts about attention sync, and also some sort of follow-up work that basically understanding quote unquote the science aspect of the attention sync, which actually feel it's very, very nice to read over.
Yeah, thank you for the comments.
Yeah, I'm curious also, like, obviously I think this work and the follow-ups were like all very useful and had very like clear impact. But I'm curious if there are still directions that you think like haven't thoroughly been explored for attention sinks, like whether that be for specifically frontier language models or even for other architectures or things of this sort. It's like, is there something else that just hasn't really been done in this direction, or has it mostly been exhausted by this point? And the point now is just trying to understand like why the phenomena happens.
Yeah, I think basically this phenomenon happened because of the usage of softmax function, but it's hard to say that anything people develop in the initial neural network design can be optimal. It's very hard to say that. So there are definitely a lot of rooms to even small building blocks can be improved. Like I really enjoy some paper this year or last year, like scalable softmax or even softmax alternatives. So basically thinking about how can we improve small building blocks in neural networks can maybe fundamentally change like being the like fundamental building blocks of future neural networks.
I see.
Mm-hmm.
Do you think this would happen for any function that normalizes to a probability distribution, or is it like, is softmax special in some way?
Great question. So I think if basically the essence here is that if you ask the model to normalize everything into several numbers, you reduce a degree of freedom of the entire vector. So the model, if the model wants to learn something, it has to, maybe it won't try to restore that degree of freedom by dumping something and making something one, so that the remaining part have a degree of freedom equals to n-1. So then why not just use attention sync? You give the model a redundant token and let the model to freely model the remaining. Yeah, I think that's a pretty nice approach to solve this issue.
I see.
Mm-hmm.
Yeah, I think there are also a couple questions I can see in the chat.
Yeah, so one of the questions was basically like, what is stopping us from using later tokens as the attention sinks instead of fixing a set of like starter tokens, like for your pre-training strategy?
Yeah, so if you use some later tokens as attention sinks, for tokens before that token, these tokens cannot attend to that attention sink. So like if you use the if you use a token number 1,000 as attention sink, which means thousands of tokens cannot attend to that token cannot use that sync. It makes model very inefficient. So the most efficient way to for the model to learn is to use the first token, which is globally visible as attention sync.
Actually, I don't think there were any more questions. I think everything else is just like a comment. Yeah.
Comments from.
But yeah, thank you so much again for this wonderful talk.
Thank you.
Thank you.
Yeah.
All right. Thanks, Guangxuan, for the nice presentation.
We'll be back tomorrow, I believe, at 3 p.m. Eastern.
Yes.
For a talk on quantization by Professor Chris Desat. So we'll see you all there tomorrow. But for now, thank you all.
Thank you.
Bye-bye.
Bye-bye.
Thanks.